While estimators and having good estimates of parameters sounds really good, we're going to be wrong a lot of the time, right? These are models, and models are imperfect representations of how the world works, right? So a point estimate is okay, but it's not really useful if we don't know how much confidence we should have or what the bounds around that estimate should be. So what we're going to do is we're going to use interval estimation. By that, I mean we are going to construct confidence intervals. So for a population parameter, a confidence interval, you can think of it as kind of a range of numbers within which a parameter is believed to fall. So you have probably heard of a confidence coefficient, and that's the probability that the interval that we have contains the parameter with repeated sampling. So you've probably seen like 0.95 as a confidence coefficient, which is a 95% confidence interval. That is usually represented as statistically reliable in academic literature, although there is no reason that that is the gold standard per se, other than that's what the NIH uses for funding of trials, and that's what a statistician in the early 20th century said was a good indication. But otherwise, there's not anything special about 95%. So we are going to learn how to construct any type of confidence interval, regardless of whether it's 95 or 70. The way that this is going to work is that assuming that we have a large enough sample, we are going to use the sampling distribution of, in this case, the mean of y to calculate some bounds around that population parameter. Remember, the parameter is represented by mu, the estimator is represented as mu hat, assuming, right, that y bar is normally distributed such that it's centered around mu and has standard deviation equal to sigma. You'll remember that sigma is going to be equal to sigma hat in this case because we need to use the sample standard deviation as our best guess or stand-in for the population parameter. Now, once we have a general understanding of the difference between the parameter and the estimator, then we can just kind of plug in these values for both y bar as well as sigma. Once we have that, then we know what the estimated sampling distribution is, right? It should be centered around y bar with the spread equal to sigma hat. We'll use our knowledge then of the normal distribution to find a confidence interval. So we're invoking a central limit theorem here and using what we know about that, as well as the sampling distribution of y bar, to make some bounds around how that data is spread. So we want to know what the 2.5 percentile is at the bottom and at the top. We want to know what's the probability of being outside of that interval on the top and the bottom. To do this, we're first going to obviously calculate y bar. Then we need to calculate the sample standard deviation so we can get sigma hat. Then we need to think about how much area do we need under the curve to the right or the left. And that's going to depend, right, on, in a lot of cases when we're doing hypothesis testing, we're going to want to know, is it the top or the bottom tail? With confidence intervals, we need to know both sides, right, because we're trying to create bounds around that parameter of interest. Once we have figured that out with regard to the spread and how far those bounds go, that's going to give us a z-score, and that's going to be associated with that spread. We're going to use these values in conjunction with what we know what the mean is to create the bounds or confidence intervals. We can do this in R manually, and here that's all I'm doing. I don't really want to walk through this too much. If you're interested, please go through the slides later. But all this to say that easily in R, we can construct a confidence interval around a mean if we have the sample mean and the standard deviation. Now, although this is nice and we can come up with the bounds, the most important part of this class is going to be interpretation. So what does this exactly mean? This means with repeated sampling, we believe that our parameter of interest would likely fall within these bounds. And specifically, you can think within 100 repeated samples, we imagine that the true population mean is going to fall within these parameters 95 out of 100 times. And the only reason that we can say this is because we are making assumptions about how that variable is distributed with regard to the central limit theorem and a normal distribution. So to wrap things up, please read all of the required and suggested online materials. Problem set number 1 is up on GitHub. Please ask if you have any problems accessing that or compiling any of your code. All of the slides, as usual for these lectures, are available on the course website as well as Canvas. And in the next module, we're going to move from using point estimates and confidence intervals to some sort of hypothesis testing, which is really fun because that's our first type of statistical inference. All right.